It's an invisible force that we put to work, trapping bubbles in a soft drink, turning liquids into foamy cream, and generating the most damaging force in an explosion. Get ready to spend some time with modern marvels under pressure. Pressure is hard at work all around us. An invisible force that makes things move faster, change consistency, or raise and lower temperature. Pressure is often hard to see, but it can be measured, whether it's in liquids, in solids, or in gases. Pressure is registered in pounds per square inch, or PSI. That's literally the weight of 1 pound pressing down on 1 square inch. Add weight, and the pressure goes up. The water that comes from your tap, that's about 35 PSI. The water shooting out of a fire hose, about 100 PSI. Nobody understands the power of PSI like firefighters. Engine 22 of the Danbury, Connecticut Fire Department is a state-of-the-art mobile firefighting platform designed to do one thing: generate flame-killing water pressure. Lots of it. Engines like these are technological marvels, capable of delivering more than 1,200 gallons per minute via multiple hose connections. That's because the engine's internal pump creates enormous pressure that can push water out at top speeds. Engine 22 only carries 500 gallons, so these high-pressure hoses are going to need more water, fast. In most fires, that water comes from a fire hydrant. A 5-inch diameter supply hose locks into the town's water system. The pressure is on, and the hose springs to attention. But municipal fire hydrants are unpredictable, delivering water at varying pressures. So the fire engine itself juggles the inflows and outflows, keeping the pressure constant. Tackling a fire from a ladder truck adds another layer of complexity. The engine has to generate additional PSI to compensate for its height over the ground.
22 driver, 24, water's on the way.
It's like pumping 1,000 gallons of high-pressure water up a steep hill every minute.
You have a big fire, you need big water.
Firefighters can't handle this volume of water by hand.
We could unsheathe all the shingles off this roof. You're putting 1,000 gallons of water out at 80 pounds per square inch. That's a lot of force. It's an awesome amount of power.
Nothing is more critical to this high-pressure offense than a strong defense, and it comes from a fire hose. A flexible cylinder lined with synthetic rubber.
This is a rubber extrusion machine. We're making a tube liner. So the rubber actually works really well in the fire hose because it enables the fire hose to dilate and swell and stretch under pressure. It also obviously provides sealant for the water to transfer.
All-American Hose in western Pennsylvania uses about 2.5 tons of synthetic rubber every day. This liner will fit inside a sturdy outside covering made of tightly woven nylon. The weaving machine spins at 100 RPMs. The weave is so tight, the machine's output is only 2 feet per minute. After weaving, each jacket is manually inspected for any defects that could cause the hose to weaken and burst under firefighting pressures. The jacket and rubber liner come together on this 100-foot-long table.
A fire hose is usually made of three sections. One is the inner rubber liner, which we insert into the inner jacket. And then we take that inner jacket liner assembly and we insert it into an outer jacket. That protects the hose whenever it's under pressure. It also protects it when it's under fire conditions.
Pressure seals the deal with an 80 psi hot steam treatment for 15 minutes. The steam expands the hose to operating size for the first time and activates an adhesive that binds the inner layers together. The steam, heat, and pressure make the fire hose even more rugged. With the addition of alloy couplings, the fire hose is almost finished. But first, it must endure a proof test where it's subjected to 800 psi. That's 2 times greater than the maximum that firefighters will ever need. Why? Because pressure can spike unexpectedly when hoses are twisted, crimped, or run over. Some hoses undergo an additional burst test over 1200 psi. That's enough to break them open. But the way this hose is designed to burst, along its seam, it could handle even that.
Pumped up the hose to the burst pressure, and when the hose bursts, we want it to burst longwise so it's safe like a banana. If it bursts in the cross section, then it can be a loose cannon. You could have hose flying all around.
It takes more than 1200 psi to burst this hose, a key test of its ability to withstand enormous pressure. But even to those of us not battling fires, water pressure plays an essential role. When you turn on the tap and water flows out, it's thanks to water pressure. But how does water pressure work? And why is it so reliable? As a liquid, all water naturally flows downhill, picking up power and pressure as it travels. It's the same basic way water gets to your house. A water tower is simply a large water reservoir, elevated to generate pressure and propel water into your kitchen sink.
Water towers use the most patient force I know, and that's gravity. All you have to do is rely on the mass of water to push it through the pipes, and for the most part, you're in pretty good shape.
Your typical water tower holds more than 1 million gallons, but its height is its most important feature. For every 2 feet that water is raised off the ground, it contributes 1 more pound of pressure, or PSI, to the system. A water tower must be tall enough to push water through a network of pipes and into surrounding homes and businesses. Most cities aim to generate pressure between 50 and 100 PSI. Water towers are usually taken out of service for maintenance once a year. This gives us a rare opportunity to step inside its pressure-creating construction. This tank is over 90 feet in diameter, and it can hold 1.5 million gallons.
When the tank is full, there would be 35 feet of water above us.
In Loudoun County, Virginia, Caldwell Tanks is now constructing what will be the country's biggest water tower site. These 2 massive 3 million gallon towers are half steel plate and half reinforced concrete.
The pedestal has a diameter of 64 feet and 12-inch thick walls all the way around. The pedestal height is on the order of 110 feet, including the dome that is on top of the pedestal.
When it's completed, the 500-ton tank will be hoisted up to the pedestal's dome and locked into position. This 116-foot diameter tank will deliver 50 pounds of pressure into the local water system, serving 15,000 households. But what happens to your water pressure if you live in a building that's taller than the highest water tower? That's a problem that New York City first faced more than 100 years ago, when it began to grow taller. There wasn't nearly enough water pressure for the topmost floors. The solution became an icon, a water tank for every building over 80 feet.
Water tanks are old school, but they still work.
Water tanks like these are replaced every 25 years. The job has to be completed in less than a day. A challenge American Pipe and Tank is ready to take on.
While this tank is empty, this building has no fire protection. So it's pretty critical that gets back online as soon as possible.
The team spends the first 2 hours dismantling the old water tank.
That's it.
Next, they assemble a barrel large enough to supply this 9-story building. 5,000 gallons should do it. The team erects a circle of staves and then tightens them into position by a series of hoops. All of this while dangling more than 100 feet over the pavement. In New York City, all water tanks, old and new, are made of wood.
Wood is a great material for an outdoor water tank. Wood is a natural product. It breathes. It does very well outdoors. When you actually look at this tank from the top, you will look down and you will see a true circle, perfectly milled and installed like a big jigsaw puzzle.
Like all water towers, once completed, the tank will require very little attention to do its pressure-generating job.
The water tank is a very maintenance-free type of system. A small pump in the basement fills the tank and gravity just does the rest.
While New Yorkers are proud of their rooftop water tanks, some landmarks prefer to keep them out of sight. The Empire State Building was one of the first skyscrapers to hide its water up top. So even if you don't see them, water towers and rooftop tanks are up there, providing constant water and steady pressure. Countless aspects of our everyday lives are under pressure. We harness water pressure and store it high in the air until we need it. We bottle up air pressure and hold it in aerosol cans. It may be everywhere, but pressure is not always under our control. Explosions. This is pressure gone wild. An explosion causes rapid expansion, which gives birth to an unpredictable pressure wave that can travel over long distances. But what's really going on here? Imagine a pebble dropping into a pond. The ripples move out at a steady pace. An explosion is something like this, but in the open air, and not at all steady. Shock waves from an explosion can only move as fast as the speed of sound, so they bunch up, and that's what creates a wallop-packing pressure wave. But pressurized gases aren't always destructive. On a much smaller scale, we even bottle air's explosive pressure and enjoy it, bubble by bubble. Avery Beverages has been putting the pop in soda pop for more than a century.
If you want to see what 300 pounds of pressure is like, I can open a valve here. It's pretty loud, though. I'll warn you ahead of time.
Rob Metz is the mastermind who keeps these decades-old machines running.
We're an old-fashioned soda company, and it's, as you can see, handmade. And we still make our soda the way it was done years ago.
That means first mixing up a batch of flavored syrup, and then adding the other half of the recipe, the fizz. The bubbles in a soft drink are carbon dioxide, or CO2. That's why we call the process of putting the bubbles in carbonation. Pressure plays a role in every step. Avery stores their CO2 in a liquid state, under 300 pounds of pressure, at 40 degrees below zero.
This is where we control the amount of pressure going into the carbonator, and this is where we adjust it for the different flavors. For fruity flavor, we're going to have it running around 60 pounds per square inch. For a higher carbonated, a mixer or a cola or a ginger ale, we're going to run it at about 80 pounds per square inch.
Higher pressure means more bubbles. And you heard right. Colas contain more bubbles than fruit-flavored sodas. That's simply because we like our colas much fizzier than other carbonated beverages. So how does CO2 find its way into water?
Coming in the top here is our water line, and in the side here is where our carbon dioxide comes.
Normally, you can't see the moment when the fizz goes in. Here, inside the carbonator, pressurized carbon dioxide is forced into the water, and a unique reaction occurs between the water and the gas.
Carbon dioxide is special because it dissolves in the water. You can get a lot more CO2 into a bottle like this one than you can nitrogen or oxygen, and that's because the CO2 is more soluble.
By the time it's done, this water will have absorbed 3 times its own volume in carbon dioxide. That is a lot of gas. And the higher the pressure, the faster the gas dissolves into the water. The soda finally comes together at the bottling station, where the flavored syrup gets dispensed and mixed with the carbonated water under pressure. Then a capper seals it off and traps the CO2.
When they get down here, the syrup and the carbonated water aren't mixed. So every bottle is going to be inverted 3 times. 1, 2, 3. And then they're mixed to stay mixed. So that's what's happening over here.
Now it's time to sit back and enjoy. Just don't shake things up. Soda pop is by no means the only beverage in which we find CO2 bubbles. A celebratory champagne pop? That's the result of CO2 escaping the bottle. Shake the champagne, and you excite the gas, creating a surge of bubbles and pressure. Even agitated, much of the CO2 remains. There's still plenty of fizz to be enjoyed. But what if nearly every single CO2 bubble in a bottle is forced out, all at once? That's what you're seeing here in the infamous Coke Mentos explosion. A roll of candy is dropped into a bottle of cola, and the pressure release is downright explosive. How does it work? Most scientists believe that the unusual surface of the candy spurs a rapid chain reaction to bubble formation, in which each new bubble creates even more bubbles, and an instant release of all the pressure, until the bottle is out of gas. So the explosive froth is all the carbon dioxide leaving the bottle at once. Like an explosion, there's lots of pressure, but it's released at a much slower rate. No pressure wave, no damage. Just one big mess. Pressure kicks off many of our days. It's the driving force behind another foamy mess. Only when this one blows up, you put it on your face. When Barbasol was invented in 1919, it was the world's first shaving cream. But it didn't become the fluffy stuff we know today until the 1950s, with the advent of the pressurized aerosol can. Before shaving cream, men had to lather up with soap. Shaving methods have evolved since then, but the materials, not so much. A visit to a Barbasol plant in Ohio reveals that shaving creams still share a key ingredient with soap: stearic acid. It starts as flakes, but it slowly transforms into a liquid as it heats to 150 degrees. Emulsifiers, sudsing agents, and filtered water are combined with stearic acid in massive 3,000-gallon mixing tanks. The pressure is yet to come. Over 10,000 empty cans enter the production line every hour. A 12-head filler processes 180 of them a minute.
Well, the shaving cream at this stage pretty much looks like, I would compare it to skim milk. Fairly watery and cloudy. It's not until the propellant goes in the can that it gets the foamy, rich texture.
Once valves are crimped to the top of each can, they're ready to receive pressure. But for that step, the entire production line makes a detour out of the factory building. The pressure is injected in a gas house that's separate from the factory. Barbasol uses two gases as propellants, propane and isobutane. Both are potentially explosive, which is why this process is done outside the factory walls.
So if there were a spark present, the roof would actually get blown off the building and this room would get foamed to suppress the fire.
The amount of propellant in a single can is not enough for a consumer to worry about.
Once the cans leave this building, they are under pressure.
The cans return to the factory under 80 psi. Then they run through a hot bath to ensure that there are no leaks. The heat increases pressure to over 100 psi, simulating conditions the cans might encounter during shipping. But how does shaving cream go from the consistency of skim milk to this? You have to understand what's going on inside the can. The propellant gases mix with the soapy solution. Under pressure, they become a single liquid. When the valve opens, the pressure pushes the liquid out and foamy cream emerges.
The material, the propellant, is above its boiling point at room temperature. As a result, when I open the valve, I release the pressure and the propellant boils. That small amount of liquid turns into a huge amount of gas, and that's the way you're able to get a large amount of foam into a small can of shaving cream.
So inside a can of shaving cream, pressure reveals what a versatile force it can be. Once you start looking for it, pressure is just about everywhere. From the mundane to the critical. It plays a role in nearly every job. Cut something, and it's pressure that does the work. It doesn't matter what's in your hand or what you're dividing. The best cutter in the world employs blistering pressure. Yet it's cutting with nothing more than water. It's a great demonstration of the incredible power of liquids under pressure. But where does all that force come from? Jet Edge Water Jet Systems has built a machine that puts water under massive pressure. It's called, appropriately enough, a water intensifier system. A hydraulic pump turns at 100 horsepower, generating 3,000 psi. This pressure is transferred to a cylinder that uses a piston to put 75,000 pounds of pressure on water. If 75,000 pounds of pressure per square inch sounds like a lot, it is. Consider this. Nuclear subs can't survive deeper than 2,400 feet in the ocean, where the pressure is a little more than 1,000 psi. Water exits the nozzle at Mach 2, roughly 2,000 miles an hour. That's faster than a bullet exits a gun. A jet of pressurized water has a lot in common with another high-tech tool.
The ability to concentrate this stream of water into a very small area, it's kind of like using water as a laser, because that's what a laser beam also does as well.
The precision of a water cutter is unparalleled. The water jet blasts through a sheet of carbon fiber as if it were butter. And it'll do the same to 12-inch steel or titanium.
First of all, the water acts as a lubricant. And second, it also acts as a cooling agent to take some of that heat away.
Unlike a water jet, other cutting devices generate heat, which can warp the material or make it brittle. A water jet is unstoppable. In fact, if it weren't for a 2-foot deep bath of water underneath the material being cut, the water jet would be carving holes in the factory floor.
Water can cut a number of things. You can cut sheet metal, foam, rubber, but if you want to cut something really thick, like say 6 inches of titanium, then you've got to add garnet abrasive. And that is this stuff right here.
The abrasive adds erosive power to the pressurized water and accelerates the cutting. Water jet cutting has been a boon to industries like auto racing. Michael Waltrip Racing fields multiple teams on the NASCAR circuit. They build dozens of cars in their North Carolina facility every year. Custom parts cut by high-pressure water are used every step of the way. Removing the engine reveals all the parts cut by the water jet.
Here we have a bare chassis. We can see a large number of components that we cut from the water jet, from our engine mounts here and on the back of the engine. Suspension pickup parts are all cut from the water jet. We've got steering arm braces where the steering connects is all cut on the water jet.
The water jet cutter shapes the parts quickly and to an engineer's precise specifications. When you're traveling at over 200 miles per hour, where failure can be a matter of life and death, you want to know that every part works perfectly. By machining parts flawlessly, a water jet cutter makes racing safer. Pressurized water is ideal for cutting, and pressurized air can be just as useful. Although it lacks the weight of water, air pressure can turn into something that'll blow you away. With a sandblast, these machines clean the toughest surfaces, all powered by compressed air. Nothing beats a sandblaster at scouring paint or grit and grime from old parts. And just like with a water jet, the secret ingredient is another gritty abrasive that's driven by pressure.
With pressurized media, you don't have to go anything over that. I normally recommend 90 to 100 for blasting. When it gets fully decompressed, that handle will drop, and that tells you you're ready to fill. Now you're ready to fill.
If a 100 PSI sandblaster sounds lame compared to the pressures of a 75,000 PSI water jet cutter, it's not. At 100 PSI, a sandblaster will strip naked skin to the bone. Bad Boy Blasters, manufacturers' custom sandblasters, and every single one relies on pressurized air. But blasting with abrasives is a dirty, dusty job and can require a lot of cleanup. They've invented a vacuum that sucks away the abrasives and paint as fast as it can be blasted. The paint dust stays in the air filter.
Turn on the vacuum. Now you can see at the 120 PSI, this is running a 40-60 grit. How nice of that's a good paintable surface.
A self-contained blast cabinet made of welded sheet metal makes sandblasting even less messy. Sandblasters are highly efficient, yet despite the name, they don't use sand. Sand can cause silicosis, a potentially fatal lung disease. Most industrial sandblasters like these now use aluminum oxide, the same material commonly found on sandpaper. Aluminum oxide can survive multiple runs through a blaster.
You can blast anything. I got people doing anything from blasting glass, doing designs, metal parts, a lot of aircraft industry work.
It may not pack the punch of a water jet, but a blast of air pressure is all it takes to turn an old hunk of metal into something shiny and new. Pressure is everywhere. Just look up. The atmosphere rises more than 20 miles over our heads. And all that air has weight. A very precise weight, in fact. 14.7 pounds. That's how much is pressing down on those of us who live at sea level all day, and we hardly notice. But there's something that does get our attention. Atmospheric pressure lows and highs. We know it as weather.
Air pressure has a lot to do with weather, and particularly it has a lot to do with wind.
Check out any weather map. The highs and lows are air systems seeking to equalize pressure. Wind blows from areas of high pressure into those with low pressure.
If you want to think of it that way, the more steep is the drop-off. From high pressure to low pressure, the more severe is the weather.
Up there, it's a maelstrom of varying pressures, temperatures, and humidities. And in extreme cases, it turns deadly. But air doesn't exert nearly as much pressure as the other substance that rings our planet. Water. 30 feet of seawater creates the same amount of pressure as 20 miles of air. Some of the most destructive forces humans must overcome are in the deep sea. At just 100 feet, water pressure crushes an empty water bottle. That's how much the air inside it is compressed. Of course, you wouldn't be seeing images like these at all if it weren't for divers with video cameras.
We're under a lot of pressure. Time pressure, water pressure, to do a good job.
Highly trained underwater cameramen like Bob Cranston put their bodies on the line every time they dive. And the video gear they take down with them is worth tens of thousands of dollars. For divers, crushing pressures are the enemy.
And what we're feeling when we go in the water is the weight of the water over our head. The deeper we go, the more pressure there is.
Waterproofing alone won't do it. The only way you can take a camera underwater is by using a pressure-resistant shell called an underwater housing. Gates Underwater Products designs housings for all types of cameras. The process involves a series of trade-offs. The shell needs to be big enough to fit the camera, yet cylindrical in shape to resist pressure. The fewer the parts, the fewer things that can go wrong. The main section of the housing emerges from a 65.5-pound block of solid aluminum. Machines remove 88% of the metal, leaving a hollow 8-pound cylinder. Then it's on to the tumbler, which polishes away any sharp edges with synthetic rocks and water. But even if all parts are perfectly machined, a seal can always fail due to human error.
The user has to do a visual inspection to make sure there is nothing on the O-ring that can compromise it. Something as small as, say, a human hair laying across the O-ring can allow water to pass at that point.
Large silicone O-rings seal big openings against pressure. And tiny sleeves, called glands, employ a double set of seals to maintain pressure on the knobs and shafts that control the camera. As the last step before plunging into the crushing ocean, workers test the housing's ability to survive. First, they test for normal pressure by sucking all the air out of the housing.
Now we wait to see if there's any changes in the numbers on the pressure gauge.
If normal air pressure can't find its way into the vacuum in the housing, then it's ready for a much more serious pressure test.
The housing didn't lose any pressure, it's perfectly sealed.
But how will it do when the pressure is multiplied?
So now I'm adding pressure to the tank, which will bring us up to at least 100 psi, and simulate our dive to about 225 feet.
Thorough leak testing requires putting every moving part to the test.
I'm looking for any water that might be in any control shaft or around any sealing areas. And we'll actually torque on some of the controls to make sure that we have nothing in and around the control glands themselves. Checking around the port area. This one passed the test.
Down here, minimal visibility makes gathering images even more challenging. Gates camera housings can perform in waters as deep as 450 feet, where the pressure is more than 215 psi, about 15 times greater than it is on the surface. Even at 100 feet, the psi is 4 times greater than at the surface. A crushing force that also challenges a diver's body.
The ocean applies pressure on all air spaces. Our lungs have air inside of it. Our mask, our ears, all of these areas have to be equalized in our body. Otherwise, we feel squeeze and pain, and it's a bad thing.
Even the air coursing through a diver's bloodstream changes with the pressure. This is one of diving's greatest hazards. Every minute a diver spends underwater, his blood absorbs more foreign gases, like nitrogen. If he ascends to the surface too quickly, dissolved nitrogen bubbles will turn back into gas, just like CO2 in a bottle of soda pop when it's uncapped. This potentially lethal phenomenon is called the bends. Divers can use a computer to calculate the amount of pressure they're exposed to and calibrate a slow return to the surface. Coming back from a deep dive may take hours of slow decompression. So every diver knows that pressure is a force to be reckoned with. Pressure is everywhere. It's there when we need it. But when it's out of control, it can be brutally destructive. It can be our worst enemy underwater, but then we turn around and use it as the most powerful tool in a factory. Pressurized cans throughout your home, they not only deliver foamy lather, they can also dispense some tasty treats. Whipped cream isn't the only food that's created with the help of pressure. A kernel of corn pops when the water within it turns to steam. Water expands 1,600 times when it becomes steam. In an enclosed space, that creates an incredible amount of pressure. The Industrial Revolution changed our world, but it could only happen after we'd harnessed steam pressure. So what happens if we bottle up that steam and put it to work in our kitchens? This place has almost as much in common with a science lab as a kitchen. In fact, they call it the cooking lab. The team here researched and photographed a multi-volume book called Modernist Cuisine to reveal the science behind cooking and to discover new techniques.
We use high-end technology to play with our food for the purpose of making it more delicious, more interesting.
Pressure is one of any kitchen's most versatile tools. Many homes have pressure cookers, but most of us take them for granted, rarely stopping to think about how they work. When you cook in an open pot, liquids can never get any hotter than 212 degrees Fahrenheit, the boiling point of water.
The pressure cooker is a fascinating piece of equipment because it allows us to cook in a high-pressure environment. We increase the pressure to 15 psi 1 bar, and that's in extremely pressurized environments.
The pressure is now twice as great as normal. It's equivalent to being 30 feet underwater. And what's strange is that the water isn't boiling. It'll only do that when the temperature surpasses 250 degrees, 38 degrees higher than the boiling point at normal pressure. That extra heat can brown meats or caramelize vegetables faster.
Increasing pressure can speed up cooking, create new flavors, and really facilitates the cooking process in general.
Pressure cookers have been around for more than 100 years, but they haven't always had safety features. Today, the lid is held in place by heavy flanges. A rubber gasket forms a hermetic seal. And if the pot overpressurizes, a safety valve vents the excess pressure.
It will never explode. It will just release all that steam, and it will be safe. And now it's very upset.
Steam pressure not only cooks, it can also be put to work sealing food for long-term storage.
So this is a pressure canner. Some of the features are a little bit different than a traditional pressure cooker.
A pressure canner is basically a pressure cooker on steroids. It can withstand almost twice as many psi as a pressure cooker. Rather than a rubber gasket, it has a metal-to-metal seal that requires heavy clamps to bolt it down and hold it in place. The pressure canner also works double time. It sterilizes jars while sealing them. The process of heating and cooling the jars leaves them with a perfect vacuum seal. These pressure can tomatoes can survive for centuries on the shelf. Another pressure cooking technique was perfected to send food into space with astronauts. It's the opposite of cooking under pressure. This is cooking in a vacuum. Flavor, texture, and freshness are all preserved as water is drawn out under less than 1,000th of a pound of psi. This is what's called freeze drying.
These carrots are very light. Only 1 to 4% of the water that was already in them is still there. So it's very, very, very dry.
Once reconstituted, these freeze-dried veggies look like something you'd find in a cup of dry noodle soup or ramen.
So with freeze drying, we're manipulating pressure to investigate the future of cooking.
Lightweight dehydrated foods are perfect for outer space, where every ounce of launch cargo is carefully managed. In fact, one dish, freeze-dried ice cream, was invented for NASA and flew on an Apollo space mission in the 1960s. And it's all thanks to the incredibly versatile force we call pressure. We use it to build and destroy, to rescue, to restore, and to explore. Wherever you go, and whatever you do, pressure will be right there with you.